Hello everyone, my name is Minh Duc, and this afternoon I'll be giving a workshop on the use of FactSage for simulations on aluminum alloys. So this morning I gave a presentation for my master's project, and in it I gave some of the challenges for the aluminum industry, most notably the rising impurity content in alloys because of the decreasing quality of anode-grade coke. This combined with ever-increasing demand for performance and the need for recycling means that impurities must be controlled. One of the tools we have is thermodynamics. With it, we can predict the impact of impurities, the phase formation, and the microstructure of alloys. This makes FactSage a powerful tool for alloy design and alloy production and recycling. So in this workshop, we'll be looking at 3 specific examples of the use of FactSage. In the first one, we'll be looking at the cooling or solidification simulation of a specific aluminum alloy, just to see the phase assemblage and the variant reactions that occur during the process. In the second example, we'll be looking at the impact of impurities in the solidification, more specifically to look how this impurity will partition in the phases that are present in the first example. And in the final example, we'll have a brief introduction to cathode modeling, more specifically looking at the solution module. Let's begin with the cooling or solidification simulation. So for this example, we'll be using a 5000 series wrought aluminum alloy. I've pulled from MathWeb the composition spec, as you can see on the table on the left, and we'll be using these values for our cooling calculation. So once you first open the equilibrium module, you'll be taken to the reactance window, and this is where you put in the composition information of the alloy. Now, because the software takes in absolute values of mass or moles, we will have to use a base of 100 grams for the element inputs, and we'll also have to change the units because right now it is in moles. So if you click here on the bar here, you can select grams, and we'll also take Celsius for the future. So now we are in grams. We can put in the first element, which will be aluminum. Then using the plus button here, we can put in the other element, chromium, and so on and so on. So for the quantity here, using our base of 100 and a maximum spec of 0.25 weight percent, we can put in 0.25 grams. Now I've already done this, so I'll use one other feature, which is you can save your compositions. And then here I'll just load the one I made for this workshop. Go back to the reactance menu, and here you should have the final composition for your alloy. Now, of course, adding more elements will mean longer calculation just by the sheer amount of species that the program has to consider. So you may want, in some cases, to reduce the amount of elements that if you consider them negligible. Choosing the right database is an important part of this simulation. So for our example, we'll be using an aluminum alloy. So we'll be using the FT-Lite database right here. It is possible we might also encounter gases, so the right database for that will be the FactPS database. Now on the left you have all of the different databases that are provided by FactSage, and on the right you have the databases that the user can generate, and we'll have more on that on the third example later in this presentation. Now once you selected all the right databases, you can click OK, come back to your reactance menu, and then click Next. Depending on the reactance and the databases selected, in the menu window you'll be presented with all of the possible compound species and solution phases that could appear in the cooling calculation. So first, with the compound species, you can select gases, pure liquids, and pure solids. In this situation, we'll select the gases and pure solids only, because the pure liquids will be included in the liquid solution. Now if you right click on in the pure solids, you'll be presented a list of all the possible compounds, including the intermetallics if you scroll down, that are in FT light. You can also manually select and deselect some compounds if you wish to do so. In this situation, we'll keep them all selected. Now on to the solution phases. So this is where the selection is important, because it can drastically increase the calculation time if we simply select all phases. So the first step, we will still select all of the solutions just to see how many species will be considered. In this case, it's above 4,000 species. And if we consider as well the compound species, we reach almost 4,300 species. Now we can reduce this number drastically by just eliminating the dormant phases. The dormant phases are still taken into account in the calculations, but will not appear in the final phases. So we can just deselect all the dormant solutions. And already you can see we're now below 1,000 species for the solution phases, and a little above 1,200 species for the total phases. So now for this particular situation, there are a couple more phases we need to change because the cooling calculation cannot work with them activated. First, we have the BCC ordered and disordered transition that we need to disable, so the 2 phases here. And then we have the possible three-phase immiscibility given by the symbol J for this phase, and the cooling calculation cannot use this, so we'll just change it to a possible 2-phase immiscibility. Next, we have to specify a temperature to begin the cooling, so this will be the temperature of the liquid at the beginning. Here, because the liquidus, according to all of the elements, is well below 1,000, we can use this value, but depending on the elements you put into the reactants, the liquidus temperature may be higher than 1,000, so you would need to adjust accordingly. Most possibly with the addition of zirconium, such thing could happen. The final element to change is to specify that we want a cooling calculation. So here, using at the liquid solution phase, we right click on the eye here, and we can select on this pop-up window the cooling calculation, which is represented by the symbol L. Once you click that symbol, that option, you reach the cooling calculation window, which allows you to select between a normal equilibrium cooling and a normal equilibrium calculation, equilibrium cooling, and Shell-Gulliver cooling. The difference between the two types of cooling is mainly in the cooling rate that's used and the phases that will be forming. So for example, in the equilibrium cooling with a slower cooling rate, at every point during cooling there is an equilibrium, and as such the different phases, the elements are free to move between the other different phases until final disappearance of the liquid. In non-equilibrium cooling or Shell-Gulliver cooling, the fast cooling rate means that as phases are formed, there is no equilibrium between the different phases, and so phases generated at one point will be kept and are permanent through the entire cooling process, which means, as you can see in the figure, that the final phase is not uniform. So for this first example, we'll be looking at both types of cooling, beginning with the equilibrium cooling. Now select the option, click OK, and you can see the letter L is now next to the liquid phase, indicating that this is in fact a cooling calculation. And it's also written down here and throughout the entire menu. So now we can begin the simulation by clicking the button Calculate. The simulation time may last a few minutes depending on the number of elements in the alloy and the number of phases selected. But once it is complete, you'll be directed to the results summary page, where you'll have a recap of the elements you put in the reactants page, followed by the constituents that are produced as the cooling occurs. Till finally, if you scroll down, you'll reach a table giving you all the phases present at the end of cooling, as predicted by the simulation. Here we have a total of 7 phases, but 2 of them are in very low amount, so the DO22 and the ALMNSI alpha, that are much lower than the other phases. If you continue scrolling down, you reach a summary of the invariant reactions. Here we already see that the primary phase is not the AL matrix, but instead it is the aluminum 11 chrome 2 phase. In fact, 2 other phases appear even before the FCC AL matrix is formed, the D022 and the D2H phase. The FCC aluminum matrix only forms beginning at 630 degrees approximately. Now, if you're more of a visual person, what you can do is plot the results. So for example, using the option output plot results, you can select axis to make a graph. For example, here we'll select the amount in grams as the y-axis and the temperature as the x-axis. Then we can select the species that we want, and here we will want every species that occurs during the cooling calculation. So we can go on select all stable phases, and we have a total of 9 species selected. Click OK, and let's see what the plot gives us. So these plots present the evolution of the different phases with the cooling temperature. So on the left you have a full view with starting with the liquid at 100 grams or 100 weight percentage until the final phases are formed. And on the right you have a zoomed in that I made by adjusting the Y scale so that we can better see the phases forming under 5 grams. Once again, it's this graph shows the same results as the results page, only in visual form instead of a text file. But once again, you can see the invariant reaction and how, because the reaction is in equilibrium, that although, for example, the aluminum 11 chrome phase is the first to appear because it is in equilibrium, the composition at the end is 0 because it is consumed in one of the invariant reactions. Now we will move towards the non-equilibrium cooling. For shell cooling, the first thing we'll notice is that the temperature of disappearance of liquid is now much lower, like almost 140 degrees lower than in equilibrium cooling, and this of course changes a lot in the phases that will be present at the end of cooling. While before we had 7 phases in equilibrium cooling, now we have 8 phases, and a few phases have been replaced by other phases. Most notably, we now have the tau phase and the beta phase that are appearing, as well as the aluminum 11 chrome 2 phase, which in equilibrium cooling disappeared, while it is now present according to the calculations at the end of the cooling in a fast cooling rate. For the invariant reactions, we still have the primary phase being AL11 Cr2 at the same temperature. Once again, there are 3 other phases forming before the FCC matrix. But we also note that the FCC matrix forms at a lower temperature compared to the equilibrium cooling, something like 40 degrees lower. By plotting the results, we already see some big differences compared to the equilibrium cooling, most notably the formation of the aluminum matrix is extended in temperature, reaching almost the minimum scale that we set at 400 degrees. And if we zoom in at at a lower mass, we can see that the phases produced reach a maximum and then tend to stay the same until the end of the solidification. This comes back to what we said earlier for shell Goodhue cooling, in that the phases once formed do not interact with each other anymore, and so are permanently locked at their concentration. So in conclusion, for the first example, what we did is do a series of cooling calculations on a specific alloy, and this really highlights the importance of having accurate databases for simulations, because after all, this is a prediction of what we expect of the behavior in solidification. But it is important to compare with experimental data, because simulations can often deviate from reality, and one of these deviations could be other elements that perhaps we didn't consider, such as impurities. And this will be the topic of our next example, which is the impact of impurities in solidification. So for this example, we'll be reusing the same alloy as before, so aluminum alloy 5083. With the difference being adding 0.5 gram of vanadium. Now we can already see the impact on the calculations. With the number of species has jumped about 150 more, and the amount of phases increased about 20 more. Now these aren't substantial increases, so the calculation time won't be as long, but still, this for other elements this might be more, depending on how integrated the impurity is into the database. Once again, we run the simulation and we arrive to the results page. Now the first thing you can see, if you scroll down to the phases present at the end of the cooling, and by the way, this is also a non-equilibrium cooling. There are a lot more than even the non-equilibrium cooling without the vanadium impurity. We have here a total of more than 10 phases, but beyond that, the temperature of the disappearance of liquid hasn't changed compared to the pure alloy. And the invariant reactions, the primary phase has changed to the DO22 phase, not the AL11CR2 phase, which we'll see why is that later on. But the FCC phase still forms at the same temperature. So running a plot with the results that we have, we can see just the number of phases that have been added just by increasing the vanadium content. So if we plot the results from the simulation including the vanadium and then compare it with the previous simulation without containing any vanadium, we can see the which phases have been added by the inclusion of vanadium. So on the graph on the right, you can see the D022 phase, which is now the primary phase, and 3 other smaller phases. If we add even more vanadium in another simulation, we can see that the primary D022 phase is created even more and is formed at a higher temperature. Now, using the results page, we can find what exactly is the nominal composition, at least for these phases. So returning to the results page and seeing the first constituent, the D022 phase, we can approximate a composition of approximately L3V, and if we look for the E phase, so the first time it is created at the 6th invariant reaction, we can approximate a composition of aluminium 10 vanadium 1. But this time for more practical reasons, because the information that we found could be used to predict the microstructure of the alloy, which in turn will help us evaluate the mechanical and physical properties, and help as a tool for the design of new alloys. For the last example of this presentation, we'll be going in a very brief introduction of the CALFAD modeling and of the solution module. CALFAD is a shorthand for calculation of phase diagrams, and you have here the main steps of the CALFAD approach. So for this example, I've already selected the system of interest. It's going to be the aluminum silicon phase diagram. The phases present are liquid, the FCC phase, and a diamond phase. So it is a fairly simple phase diagram with a single eutectic and no intermetallic phases. We already have the experimental data for the liquidus line, and in the following slides I'll be explaining you how to choose the appropriate thermodynamic model and how to optimize the parameters to try and reproduce this phase diagram. Alright, so to begin, we've already identified the two elements of the system, so aluminum and silicon, as well as the phases present, so FCC, diamond, and the liquid. The first thing we'll need will be the thermodynamic description for these elements and these phases. So for that we need to go into the compound module and search for them. So first we can search for the aluminum, and then using the FTLite database we have all the allotropic forms of aluminum, and for that we need the three that we identified earlier, so FCC, diamond, and liquid. So when you find the proper allotropic form, this page will give you the enthalpy at 298 Kelvin, the entropy at 298 Kelvin, as well as the CP. So how we take this information is we simply click on the allotropic form and drag it to function, and repeat that for all of the phases that we need. Now that we have all the functions that we will require, we can begin with the first solution, which will be the liquid solution. So to add a solution, you just right click on solutions, you can add solution, and here we'll name it liquid with a state liquid. And for the model, this is the important part, we will choose 2-lattice modified quasi-chemical model. Now this is a model that's been developed by members of the CRCT. It is a 2-sublattice model, but the particularity is that it takes into account the short-range ordering, and the short-range ordering is treated by calculating equilibrium amongst nearest neighbor pairs, so AA pairs, BB pairs, and AB pairs for a binary system. So once we have that, we can open up the sublattices, and the liquid is only one single sublattice, but for the purposes of the solution module, we have to choose 2 sublattices. So the second sublattice will just make a vacancy, and in the first sublattice we'll have aluminum and silicon. With the sublattices done, we can create the end members. This is done so by clicking one species and then clicking another species from the other sublattice while holding Control, and then right clicking to add the end member. Now in the end member page here we have aluminum, so the Gibbs energy function for this one will be the same as the pure element, liquid aluminum. So we can go to our functions and see the function tag, which is L hashtag liquid. So we will be putting that there. And coordinates numbers here, we can put 6 and 6. This has been found to be the optimal coordinates number for the quasi-chemical model, so we'll be using these values, and then we can create the other end member. Again, using liquid and putting the right coordinates numbers, coordination numbers. And finally, we can create an interaction by selecting the 2 end members and adding a pair fraction expansion G. This value will be left at 0 for now, and when we generate the phase diagram, we'll start adjusting this parameter to fit the experimental data. So with our liquid solution done, we can move into the next solution, which is the FCC solution. So I'll just Again, naming it. For this one, we'll be using the compound energy formalism, which is also called as the sublattice model, and you can have a possible 2 to 5 sublattices. Short range ordering is not considered in this model, but it is not as important for the solid solutions. So we'll just click OK, and here we'll add, just like the liquid, we'll have the second lattice be a vacancy, and in the first lattice we'll have aluminum and silicon. Perfect, and then we'll create the end members. So for the first end member, we'll use the same trick. We need the tag, which will be FCC A1 for aluminum, and for silicon, we'll have FCC A1. And we can create an interaction if we desire to do so. Here, we'll leave this blank, and repeat the same process with the diamond phase. So we have our 3 solutions completed, and let's see what the phase diagram module gives us for the first iteration. So in the phase diagram module, we put in the components that we have in the system, so aluminum and silicon, and we can also add our private database now using the data search. So in this case, we have the test solution we selected, and we're ready to generate our phase diagram. So for the first iteration, what we have is that if we overlay the data points, is that the eutectic temperature is still too high, and to change that, what we could do is to increase the stability of the liquid phase, so therefore pushing the eutectic temperature lower. So if we go back to the solution module and go to the interaction parameter of the liquid phase, or the liquid solution, we can put in a minus 5,000 value just as an experiment to see what it does. And what we find is that by using this interaction parameter, we get an eutectic point that's much lower than on the first iteration. Here, the second iteration is the blue lines. Still, there's still work to be done on this simple phase diagram. For example, it's still not quite perfect, and the diamond phase is a bit too large, but it's still a good introduction into the complexity that is the solution module and the cathode approach in general. We still have a lot more to cover. For example, stoichiometric compounds, we still haven't shown how to create them. Intermetallic solutions, we still need to show how to produce them. And even further than binary phase diagrams, we can do ternary phase diagrams, or even quaternary phase diagrams. But to go that much further, it's evident that optimization requires a lot more data, such as phase diagram data that we have here, but also enthalpies of mixing and of formation. We have activities that we could use, solubility data for specific compounds and phases, and even heat capacities that we can measure. So this has been all for today's presentation. I hope you found some of this interesting, and thank you for your attention.